Hi everyone. Today we are going to look at one important topic in the study of numerical solution of differential equation. It's known as boundary value problem. Okay, so we know what is initial value problem. Okay, if you forgot, I'm just want to remind you. So if let's say initial value problem given as y prime equals to f of x yx. This is the problem, and the initial condition is given as y at a equals to alpha. Okay, where my a here usually is my x naught, my alpha here is my y naught. Similarly, if I have two derivatives, second order, we have f of x, y x, y prime x. Okay, y prime x, and then you can have y of a equals to alpha. Okay, this is the initial condition. Now what is boundary value problem? Okay, so for second order, I'm just going to consider second order. We have y double prime equals to f of x y x y prime x. Okay, we have the 2-point boundary value problem. So we have y a equals to alpha and y b equals to beta. Now let me just tell you again that this is my x naught, y naught, this is my xn not equal xn, and the beta here is equals to yn. Okay, so you're looking at the interval of x from a to b. Okay, so this is 2-point boundary value problem. Okay, don't worry about the first point boundary value problem, because the first point boundary value problem you can use Laplace transform to solve it. Okay, we're looking at numerical method to solve this boundary value problem. Now in the standard form, I can write this boundary value problem as y double prime x plus px y prime x plus qx y x equals to fx. Okay, this is a standard notation for the second order boundary value problems, because the condition are given from at point A is alpha and at point B is beta. Okay, this is my x naught, this is my xn. Okay, so this boundary value problem has a unique solution if px, qx and fx are continuous in the interval AB. Okay, and qx is less than equal than 0 on the interval AB. Now to solve this boundary value problem, we have a method. So how to solve? We have the method called finite difference method. Okay, finite difference method. Today we're going to look at finite different methods. Okay, and we can also have shooting method. Okay, the difference between these two approach is, so what this finite different method does, it convert the problem, boundary value problem, into a system by replacing all the derivatives, such as my y double prime, y prime, with something called finite different, okay, with finite difference approximation. This is what finite different method does. Okay, so it converts the boundary value problem into a system. Okay, this is the key word here, system. Into a system of what? System of algebraic equation. Okay, system of algebraic equations by replacing, not replaying, replacing all the derivatives with finite difference approximation. Okay, and what does shooting method do? Okay, shooting methods on the other hand, okay, it convert the second order derivatives into system of first order linear equation. Okay, so you're given a boundary value problem, it convert into system of first order linear equation, where now you will solve using initial value problems. Okay, so so once you convert it, you can use any RK method to solve. You can use any RK method or linear multi-step method to solve. Okay, because you have an ODE, initial value problem, you can use RK method. Okay, so for today's lesson, today's topic, we're going to look at finite different method. Okay, so how can I find this finite different approximation? That's what we're going to look at today. Okay, so shooting method maybe some other day. Okay, so we have finite difference approximation. So to do this, we have to recall the Taylor series expansion. Okay, Taylor series expansion of y at x plus h is given at yx plus hy prime x plus h2 over 2 factorial y double prime x and higher order term. Okay, and if you have yx minus h, we have yx minus, h is now negative, hy prime x, h squared, negative h squared is positive, and then we have higher order term. Okay, so to get the first order finite approximation, or the first order equation first, let's look at only the first order equation here. So you can have look at, let me just label it equation 1, equation 2. By looking at just equation 1, okay, considering only the first derivative here, so we have yx plus h minus yx equals to hy prime x. So y prime x equals to y x plus h minus yx divided by h. Okay, so what we have this is actually also known as Euler method, or something called forward difference formula. Okay, now looking at equation number 2, this is equation 1, Now if you look at equation number 2 here, so if similarly approach, if I do yx plus h minus yx equals to negative hy prime x. Now multiplying both sides with the negative term and then writing in the form of y prime x. So negative with this term here become positive. This is positive, it will be minus yx plus h divided by h. No, I'm looking at equation number 2, so it should be x minus h. Okay, I'm looking at equation number 2, so just there must be a difference between equation number 1 and equation number 2. Okay, let me just fix this. Equation number 2 is x minus h. Okay, minus here, equation number 2. So this will be x minus h. Okay, what we have here, we have the backward difference formula. Okay, so now we have two difference formula. If you just consider the first derivative. Now, if I'm considering the second derivative, you can get two formulas out of the second derivative. So first, what you do here is if I add equation 1 and equation 2. Okay, add equation 1 and equation 2. So what we have, if I will have yx plus h plus yx minus h equals to 2 of yx. Okay, the term involving y prime cancels out. Okay, if I add them, this term cancels out. This term cancels out. And then h squared over 2 plus h squared over 2. You have h squared. So I have plus h squared y double prime x. Now writing in the form of y double prime. Okay, so don't forget h here. Okay, so we have h squared here. So what I have, write the other 2yx, bring it to the left hand side. So I have yx plus h plus yx minus h plus 2yx. Divide everything by h squared. 1 over h squared. Now I can write this as yx plus h plus 2yx plus yx minus h. We have the central difference approximation. We have the central difference approximation. Okay, now I'm just considering only the central difference formula. Okay, if you want to have the central difference approximation for the first derivative, what you do, equation 1 minus with equation 2. So yx plus h minus yx minus h. Yx cancels out. Okay, if I'm subtracting the two equations, yx cancels out. Now I will have 2hy prime. So I will have 2hy prime x. So y prime x, don't forget the 2h, is equals to y of x plus h minus y of x minus h. Just rewriting. And then divide by 2h. So I have the first derivative for the central difference approximation. Plus here minus y of x minus h. Okay, this is also central difference approximation. for the first derivative. Okay, now why this is important? Because remember, to solve the boundary value problem using finite difference method, we have to transform this to a finite difference approximation. Okay, now what that means? It means that we are going to convert this equation, whatever equation that we have written here, we want to convert it in the form of step size, like I'm dividing it into a step size. Okay, so what I want to say here, okay, this is x plus h and x minus h. Now consider I have I can divide the interval a and b into a number of equal sub-interval n of length h. Okay, you can divide it into a equal. Okay, it must be equal. And each length here is given as step size h, where what is h? B minus a over n. N number of sub-intervals. Okay, the point at a here, the point at A is my x naught. The point at my B is my xn plus 1. So we can have x1, x2, whatever after that we can have xi minus 1, xi, and then we can also have xn and xn plus 1. So these are all the points that if you divide it, okay, if you divide it in an equal length, so which means that now I can approximate my second order by central difference approximation and write it in the form of xi minus 1 and so on. Okay, so what it means here, so we have the second order. So look at my second order equation here. So we have y double prime xi. So this is, I'm looking at the second order approximation that I've written on. Okay, this equation here. Okay, this equation here. So x will become xi. Now x plus h. X plus h. So meaning I have from this value to this value, for instance. Okay, it simply mean as xi plus 1. Okay, xi minus h here, it simply means xi minus 1. Okay, so writing it now becomes 1 over h squared. Okay, we have 1 over h squared y at xi plus 1. This is for x plus h minus 2y xi, this is yx, plus y x minus h, so xi minus 1. Okay, so now I can write it in the form of a finite difference approach. Similarly, for my first derivative here, so y prime xi, I have 1 over 2h, y at xi plus 1, okay, minus y at xi minus 1. Okay, so now we have obtained the finite difference approach for the second order derivative. Okay, so put it into your standard form. If you forgot your standard form, I can write that the standard form for the 2-point boundary value problem is given by y prime x plus px y prime x plus qx y x equals to fx. Okay, so what I'm going to do here, I'm going to put these two equations into the standard form. Okay, let's do that. So for before that, what you want to do, you want to transform into the finite difference approach. So we have y double prime xi plus pxi y prime xi plus qxi yxi equals to f of xi. Okay, so we are doing good so far. Now what you do here, rearranging and substituting these two formulas into here, we have, first start with y double prime xi. So I have this whole thing here. So 1 over h squared y xi plus 1 minus 2 yxi plus y xi minus 1. Okay, and then plus p of xi y prime. Okay, y prime is this equation here. So I have 1 over 2h yxi plus 1 minus y at xi minus 1. Okay, and then what we have here, it's going to be long, plus q plus qxi y at xi equals to your function f of xi. Okay, before we simplify this by collecting the common term, so for simplicity, what I want to do here, instead of writing yxi plus 1, I am going to write it as yi plus 1. Okay, similarly, if I have yxi minus 1, another way of writing it is yi minus 1. Okay, and then if I have y at xi, I can write it as yi. Okay, this is just to make it more nicer. Okay, so I 1 over h squared yi plus 1 minus 2yi plus yi minus 1 plus pi 1 over 2h yi plus 1 minus yi minus 1. Okay, and then plus qi yi equals to fi. Okay, see, it's much easier writing in terms of I than in writing in terms of x. Okay, now collect the common term and factor it out. So what are the common term here? So we have yi minus 1, yi minus 1. Okay, and then we're going to collect the term involving yi, and then we're going to collect the term involving yi minus 1, yi minus 1. Okay, so you're going to factor it out. So let's collect yi plus 1. So we have 1 over h squared. Okay, 1 over h squared. And then what else? Plus pi over 2h. This is for yi plus 1. Okay, we have considered these two terms. And then the term involving yi, we have plus minus 2 plus qi yi. Okay, again it's 2 over h squared. Okay, don't forget 2 over h squared. And then what we have here, plus for qi yi minus 1, we have 1 over h squared minus pi over 2h. Now this term multiply with this. For this term, we have yi minus 1 equals to f of I. So there's so many things I don't like here. So I don't like the denominator you have 2nh squared. Okay, 2nh squared. So what I want to do now is multiply this whole term by 2h squared. Multiply. Okay, multiply, simplify the factoring term. So what I have, if I multiply by 2h squared, I have 2 plus hpi, right? 2 plus hpi. 2h cancels out with 2h squared. I have 1h. yi plus 1, and then plus, okay, multiply with 2 times 2h squared. I have minus 4. Okay, and then plus 2h squared qi yi, and then plus multiply by 2h squared. For this term, I have 2 minus h pi yi minus 1 equals to 2h squared f of I. Okay, so I want to try to avoid any careless mistake in writing this. I hope I get everything right. Okay, if I do mistake somewhere up here, I would know when I'm doing the next step below. Okay, but so far so good. Now what you can do here, the idea of a finite difference method is to convert the boundary value problem into a system of algebraic equation. This is what we did by replacing all the derivative with a finite difference approximation. Now how does this system look like? So recall that this I is from 1 to n. Okay, I is from 1 to n. Now for simplicity again, okay, let ei equals to 2 minus h pi, and then we have di equals to minus 4 plus 2h squared qi, and then we have ci equals to 2 plus h pi. Okay, so usually what you write here, if you look at here, so if you have an interval, so usually yi will be from here, yi minus 1 will be on your left side, and yi plus 1 will be on your right hand side. So this term here, I need to change their writing. So before I change to the simplicity form, so 2 minus h pi yi minus 1, this comes first, and then the middle point, middle equation or middle form here, and then this term here. So I have plus 2 plus h pi. Where's my q? Am I missing the term? Okay, I think I'm correct. Okay, yi plus 1 equals to 2h squared f of I. Okay, so what happened next? Next, I'm going to write it in the form of ei di, and ci. So this term will become ei yi minus 1 plus di yi plus ci yi plus 1 equals to 2h squared f of I. Okay, so now let's consider solving this boundary value problem and what the given interval here. So if you know, like look at this again. yi minus 1 is my y at xn plus 1. This is y at xn minus 1. This is y at xn, for instance. Okay, so what is the value of y at xn plus 1? Okay, so we have the boundary condition here. So this is alpha, this is beta. Are you with me? Okay, this is the initial condition. Okay, this is the initial condition at x equals to alpha. Now the boundary condition at the other end is at y equals to b is my beta. So in other words, this is my A, this is my B interval. Okay, so we need to remember this. Okay, we need to remember this. So now let's consider for I equals to 1 to n. Okay, I equals to 1 to n. So let's start with for I equals to 1, we have E1 y0 plus D1 y1 plus C1 y2 equals to 2h squared f1. Okay, what is my y0? What is my y0? My y0 is alpha. So E1 alpha plus D1 y1 plus C1 y2 equals to 2h squared f of 1. So D1 y1 plus C1 y2 equals to 2h squared f1 minus alpha E1 or E1 alpha. Okay, I mean alpha is a constant. I mean alpha is not a constant, alpha is a variable, but right now it's a constant. Alpha will be a number because it's interval. Okay, and then for I equals to 2, I have E2y1 plus D2y2 plus C2y3 equals to 2h squared f2. Okay, and then similarly for I equals to 3, I have E3y2 plus D3y3 plus C3y4 equals to 2h squared f3. And then if I want to consider the term before and the term with, let's say at I equals to n minus 1, we have E at n minus 1, okay, which should be n minus 2. So there's no value of n minus 2 here. Okay, right? So y at n minus 2. Okay, this is way beyond our given boundary. Okay, and then we have plus d at n minus 1, y at n minus 1 plus c at n minus 1, y at n I plus 1 n minus 1 plus 1 yn equals to 2h squared f at n minus 1. Okay, and then remember this is way our boundary. We don't have the value here, so it's gonna be 0. It's gonna be 0. And what is n minus 1? Okay, so the only term we have will be we gotta be careful how you're gonna write this later on. Okay, so see at n minus 1. Okay, and then we have at y at n. If I equals to n, we have e n y n minus 1 plus d n y n plus c n y n plus 1 equals to 2h squared f of n. Okay, so recall that this now what happened? Okay, let's just look at this n term here. So we know this is beta. Okay, so we have beta here. So what we have here, e n y n minus 1 plus d n y n plus c n beta equals to 2h squared f n. So I have e n y n minus 1 plus d n y n equals to 2h squared f n minus c n beta. Okay, what am I doing here? So this is what I'm doing. So this whole system here, we are gonna write it in the form of a system of linear equation. Okay, now I can write the system of linear equation for the given problem that we did. So this is how it looks like. Now these are my diagonal, d1, d2, d3, dn minus 1, and then dn. Okay, now look at here. This is my y1, y2, y3, yn minus 1, and yn, and this is my function. Okay, this is my function where start with 2h squared. So let me see. So start with 2h squared f1 minus alpha c1. So we have 2h squared f1 minus alpha c1, and then we have 2h squared f2, 2h squared f3, and then dot 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 up to this one, 2h squared fn minus 1, and lastly this one, 2h squared fn minus beta cn or cn beta. Okay, it doesn't matter. And then what we have here for my above the diagonal, above the diagonal I have c1 for y2. Okay, so I have c1 here, the rest is 0. Okay, the rest is 0. And then for I equals to 2, you can see here for I equals to 2, I have e2 d2 c2. So e2 d2 c2. Okay, and then for I equals to 3, I have e3 d3, sorry, this should be c3, not c4, c3. Okay, so you know when you're wrong, when you think it's not correct. So this is c3. Okay, 0. And then what we have for my n minus 1 here, n minus 1, okay, I have en minus 2. Okay, so en minus 2 up to dn minus 1, cn minus 1. And lastly, these are all zeros, okay, and lastly for dn I have en. Okay, so these are all my zero values here. So this what we have here, it's also zero, is the algebraic system of linear equation if we use finite difference approximation. Okay, if you look at here, we have this one, a y equals to b. So you can solve for y. You can solve for y. So what you're going to do for the given system, you can use either Gauss-Seidel, okay, to solve this, or you can also use Thomas algorithm. Okay, so I will show how to solve using Thomas algorithm in my next video. Okay, to let's look at one example on how we can actually write this in the form of system of linear equation. Of equations for 1 plus x squared y prime. Okay, so second order here, equals to 2 plus 6x squared plus 2x cos x minus 1 plus x squared sine x. Okay, the boundary condition is given at y0 equals to 1 and y1 equals to 2 plus sine 1. Okay, we can have the exact solution. Okay, the exact solution yx is given as 1 plus x squared plus sine x. Okay, so this one example here, we want to write it in the form of a metric that I have explained earlier on. Okay, so the first step to do is to write the given equation in a standard form. Okay, what is the standard form? The standard form should be something like y double prime x plus px y prime x plus qx yx equals to f of x. Okay, this is the standard form. Now can I write that? Can I write the given equation? So let's look at the given equation here. So this equation here, what I can write here, this is similar to 1 plus x squared y double prime. Now the reason I gave it like that is just to trick you. Okay, obviously these are the same way of writing it. Okay, so do we have a term involving y prime? Okay, now this can be chaos here. So why is that? So if you check the equation here, okay, so we have 1 plus x squared y double prime, and then how can I get the other term involving y prime x? Okay, so the y prime x is obtained when you differentiate this term here. Okay, so this equation can be written as this term plus 2xy prime x equals to the rest term here will be my fx, where fx equals to 2 plus 6x squared plus 2x cos x minus 1 plus x squared sine x. Now I should have considered a much simpler problem. Okay, but that's okay. So just look at this one here. Now I'm sure some of you are asking, where does this term comes from? Where does this term come from? Now how can I write this term here? Okay, I see this. It's another way to write 1 plus x squared plus 2xy prime. Okay, so to answer to that, let's look at this term here. So let me put a note here. So how can I write this? So I have d over dx, okay, 1 plus x squared y prime. Okay, so why these are the same thing? Because it's something, it looks like a product rule here. So how do I do this? This is my product rule, u v, let's say. So how do you do product rule? Differentiate of this thing here. So if you recall, we have u dv dx plus v du dx, right? So let's say u is 1 plus x squared. Differentiating the v term, y prime, when I differentiate is just y double prime. Okay, and then if this is my v plus v is y prime, differentiating du dx is 2x. Did you get that? So what happened? So what I can say here, I'm sorry, I have to write it here. So 1 plus x squared y prime can also be written as 1 plus x squared y double prime plus 2xy prime. Okay, that's how exactly I got this term here. Okay, so it's not that complicated, right? But I hope you understand the concept. Now the other term that I would like to consider is now arranging. Okay, I need to arrange. Okay, my Wacom battery is dying. Let me give me a second to just connect my power to my Wacom. Okay, so far I hope you have been doing really good trying to understand this whole process of solving boundary value problem using finite difference method. Okay, so I'm not quite finished yet. Okay, I'm not quite finished yet. So what I want to do, I want to transform this equation involving this equation in the form of finite difference. Okay, so how do I do that? I will have 1 plus x I squared. Okay, what is y double prime? Okay, my y double prime, the central difference formula, which is yi plus 1 minus 2yi plus yi minus 1 divided by h squared. I really hope I'm not going to make any mistake, but if I realize there's a mistake, I'll correct it immediately. Okay, and then plus 2xi. Okay, now recall the y derivative of the finite difference. We have yi plus 1 minus yi minus 1 divided by 2h, okay, equals to fi. Okay, I'm not going to write this whole term. This for f function, just write it fi. Okay, multiplying. Okay, I don't want to make mistake like just now. So multiplying the whole term, if you remember, I forgot to multiply the function f here with 2h squared. Okay, multiply the whole term with 2h squared. So what do I get? 1 plus xi squared yi plus 1 minus 2yi plus yi minus 1 plus multiply. So first of all, this 2 and 2 cancels out. Now multiply with 2h squared. I have 2. Okay, let's don't do mistake. Now what happens if I multiply by 2h squared? H and h cancels out one term here. So I have 2h. I have 2h xi. Okay. And then we have yi plus 1 minus yi minus 1. Okay, actually I did a mistake. I don't have to multiply by I was hoping not to do mistake, because if you look at here, if you look at the term here involving 2h here, first of all, I don't need to multiply by 2. Okay, I didn't multiply by 2 here because this 2 and 2 cancels out anyway. So instead of multiplying by 2h, you have to just multiply by h. So just multiply by h. Okay, so I can repeat what I said just now. So instead of multiplying by 2h squared, just multiply by h squared. H squared. Okay, so the reason we want to multiply by 2, because we thought we can cancel out the 2 here, but the 2 and the 2 already cancels out. So multiply by h squared, I have h squared here cancels out, this whole term. Multiply by h squared, one term of h cancels out, we have hx squared, and then equals to h squared fi. Okay, now we are back to business. So, like I say, things can get a little complicated. Just bear with me. I'm almost there. So what we have here, like I said early on, we arrange the common term involving yi plus 1. Okay, so I have 1 plus, so I'm just gonna can I just expand, or I have h here? So what do I have? How can I write this? So let's collect the common term, xi squared plus hxi. This is for y at yi plus 1, common term. And then the next term involving yi, just 1 here. So we have negative 2, 1 plus xi squared yi. Okay, factor negative 2. And then the term involving yi minus 1, I have plus 1 plus xi squared, okay, for this term. And then plus or minus, just be careful here. Okay, I have a negative here, so we have negative hxi yi minus 1. I really hope there's no mistake. Okay, I can never tell there is a mistake until I do the next step. Okay, sometimes my eyes are very tricky. Okay, so I hope this is correct so far. Okay, if I want to take the negative out, do I need to take the negative out? I mean, I can take the negative out for yi minus 1. If I take the negative out, what happened here? I will have, how can I arrange this in a form of yi minus 1? Okay, and then yeah, I'm just thinking, how can I write this in the form of negative h? So okay, let's just write it again. So what we have here, so this whole term involving you have the term involving 1 plus xi, so 1 plus xi squared minus h of xi for yi minus 1 minus 2 of 1 plus xi squared yi plus 1 plus xi squared plus h of xi. yi plus 1 equals to h squared fi. Okay, so remember my fi here. What is my fi? The function of f is this whole thing here, which I am not going to write it down. Okay, but just recall this is 2 plus 6xi squared plus 2 of xi cos at xi minus 1 plus xi squared sine xi. So that's the term involving xi. Now for this reason, okay, there's two ways. Okay, I can if I want to keep h squared negative, I can multiply this whole thing negative, or I can remain like this and write the form. Okay, write the system. So what we have here, okay, if you recall properly here, so we have the term, I can say a. Okay, let ai equals to 1 plus xi squared. Okay, so I have 1 plus xi squared here, the common term here. That's my ai. Okay, ai. So what I can have here, so let's just write it back in the form of ai. So I have ai minus hxi yi minus 1 minus 2ai yi plus ai plus hxi yi plus 1 equals to h squared fi. Okay, so I've changed this 1 plus xi. Trust me, there's a reason to do this. So we want to make sure our system look as simple as possible, not that complicated. I mean, not that too many variable. So if this is true, so I can write my Ri. Now Ri can be written as 2ai. Okay, now I also want to write it as pi equals to ai minus hxi h, and then qi equals to ai plus hxi h. What's going on here? Why is there I have so many h here? Okay, so not hxi, so let me just remove this. Okay, class, please bear with me. We're making more, we're gonna write it in a more simplest form. So what happened here? So this is my ai now. Now this whole term here is my pi. And this whole term here is my qi. Okay, and this is my ri. Okay, so what we have here, we have pi yi minus 1 minus ri yi plus qi yi plus 1 equals to h squared fi. Okay, the question say write in the form of n system. So we are almost there. So what you can do, you can start by I equals to 1. Okay, when I equals to 1, we have P1 Y0 minus R1 Y1 plus Q1 Y2 equals to H squared F1. Okay, and then for I equals to 2, we have P2y1 minus R2y2 plus Q2y3 equals to H2F2, and so on like just now. I equals to n. We have Pn yn minus 1 minus Rn yn plus Qn yn plus 1 equals to H squared Fn. Now recall that this is my alpha, which is my initial y0. The y0 given as, the question say y0 equals to 1. So this is 1. Okay, and the question at the other interval for at yn minus 1, this is also equals to 2 plus sine 1. So this term here, this is my y at x at 1. Okay, so this term here will be 2 plus sine 1. Okay, so for instance now this equation will be negative R1y1 plus Q1y2 equals to H squared F1 minus P1. Okay, and this term here will be negative Rnyn plus what do I do here? Pny yn minus 1 is my initial, which is my this is 1, this is also 1, the initial. Okay, so we have Pn minus Rnyn equals to H squared Fn minus Qn, this whole thing, 2 plus sine 1. Okay, so roughly you know how your system will look like. So I can write this whole thing in the form of a matrix. Okay, in the form of a matrix. So let me just move my... Okay, so I have here, so the diagonal term involving negative Rn. So I have negative R1, Q1, P2, negative R2, Q2. Okay, I told you this can be easier if you write it in a simplified form. This will be Qn minus 1, Rn minus 1, Pn minus 1. Okay, and we have Pn Rn, and then the term involving my y, y1, y2, yn minus 1, yn, and then the function involving f. Okay, so we have the first term here. If you look at it, the first term here involving is this one, h squared f1 minus p1. Okay, so I have h squared f1 minus p1. The next term all will be just h squared f2 up to h2 have n minus 1, and then this term here is my boundary, my n boundary, fn minus qn, and the term involving sine. So I need to have more space, so I'm just gonna remove this bracket and make it longer. Okay, where is it? Okay, so we have 2 plus sine 1. Okay, everyone, so we have written the given, we didn't solve it. Okay, we are not looking at solving it first. We are just looking at writing the given system in the form of n, finite difference. Okay, so this is just the beginning. Okay, once we have done this one, the next step is to solve it. Okay, so I will explain to you about solving a much more simpler system of equation using finite difference approach. Okay, thank you for watching for today's video. I'll see you next time on my next video on how to solve using finite difference method. That's all for today. Thank you.